Okay, everyone, welcome back to part 3. This is going to be part 3 of our, what is this? This is section 17.3, finding extrema. And we're going to take a look at an application or word problem for finding extrema. And so here's our problem. It reads, suppose the labor cost measured in dollars for manufacturing a precision camera can be approximated by that function right there, where X is the number of hours by a skilled craftsman and Y is the number of hours by a semi-skilled craftsman. Find the values of X and Y that minimize the labor cost, and then find that minimum labor cost. So it looks like all we're looking for here is a minimum of a function. Okay, I can do that. All right, if I remember correctly, step 1 was to find those partials and then find the candidate points. So what is L sub X, our first partial with respect to X? First term with respect to X is going to be 3X. Second term with respect to X is 0. Third term is a negative 2. Fourth term is 0. Fifth term is a negative 2y. And that last term is 0. So there's my partial with respect to X. My partial with respect to Y. First term 0. Second term 2y. Third term negative 2. Fourth term, third term 0. Fourth term negative 2. Fifth term negative 2x. And last term 0. And I'll make this into a system of equations. So then I've got, what is that first one? 3x minus 2y is equal to 2. Take that 2 and move it to the right when you set it equal to 0. The second one is going to be negative 2x plus 2y equals 2. And it looks like this thing is perfect for substitution, or I'm sorry, elimination. So I'll just add those two together. That's going to give me x equals 4. And then I'll do some back substitution. I'll put it into, I don't know, the second equation to make that one work. So let's say I've got negative 2 times x, which is 4, plus 2y equals 2. That's negative 8. When I move to the other side, I got 2y equals what, 10? So y equals 5? Okay. So now I've got my candidate point. My candidate point is the point 4.5, or in terms of the problem, 4 skilled workers, 4 hours by a skilled craftsman, and 5 hours by a semi-skilled craftsman. But I need to make sure that that's a minimum, so I'm going to go through the steps for finding the minimum to show that it is. I'll need those second partials. So L sub x, x is going to be equal to 3. L sub y, y is going to be equal to 2. And L sub x, y would be equal to negative 2. And so then I'll build my discriminant. My discriminant for the point 4.5 is going to be xx times yy minus xy squared. So that's 6 minus 4. So that's 2, okay, which is greater than 0. So I'll go back up and look at my rules. It's a long way to go. Let's see. My discriminant was what, greater than 0? Oh man, I've forgotten already. My discriminant is greater than 0. My x-axis is also greater than 0. Okay, that's what I need to know. Whew, man. My discriminant is greater than 0, and my x-axis is greater than 0. So over here, so I've got a minimum there. Okay, so now I've shown that it is a minimum. The discriminant test tells me that it's a minimum. So then the minimum cost is when x equals 4, y equals 5, and the minimum cost is, and now I have to take those values and plug them back into that original function right here. Okay, so I'm going to bring up my calculator. And so I have 1.5 times x squared times 16 plus y squared, which is 25, minus 2 times x, so minus 8, minus 2 times y, so minus 10, minus 2 times x times y, so 2 times 4 times 5 is what, 10, 40, so minus 40 plus 68. And I get 59, so the minimum cost is 59. Okay. Now, if I remember correctly, that means, if I interpret it in terms of the problem, that the minimum cost is $59 with 4 hours of skilled and 5 hours of semi-skilled labor. That wasn't too bad. Okay, so I'm finding maxes and mins, and I'm just putting it in context. In this case, we put it in the context of some production costs. All right, well, let's take a look at our next example. I think this is our last example too. Yep. The profit in thousands of dollars that Aunt Mildred's Metalworks earns from producing X tons of steel and Y tons of aluminum can be approximated by that function right there. Find the amount of aluminum and steel that maximize profit, and then find that maximum profit. So it looks like we've got a multivariable function that we're supposed to maximize. I can do that. Step 1, I need to find those candidate points. So what are those first partial derivatives? I need to make that blue highlighter less dark. All right. P sub x is going to be, what is that, 36y minus 3x squared. P sub y is going to be 36x minus 24y squared. Now I'm going to take these two and I'm going to set them equal to 0 and make a system. So I have 36y minus 3x squared is equal to 0. And I have 36x minus 24y squared is equal to 0. Nonlinear system because of those squareds, right? So what I think I'm going to have to do is I am going to have to do substitution here. So I'm either going to have to solve the first equation for y and plug it into the second one, or the second equation for x. I think I'm going to solve the first equation for y because it looks a little better. Still not much better. All right, so the first equation for y, I've got 36y equals 3x squared. So y equals 1/12 x squared. Okay. That's horrible, but all right. And then I can substitute that into the second equation. So that's going to give me, and I'm going to come over here because it's going to be a monster, 36x minus 24 times 1/12 x squared is equal to 0. So let's do some work on this. That's going to give me 36x minus, let's see, this is going to be what? 24 times 1/12 times 1/12 times x to the 4th equals 0. If you're wondering why I wrote that out, so I could make that cancellation a little better. So that'll be a 2, that goes away, that's a 1, so now I've got 36x minus 1/6 x to the 4th is equal to 0. Looks like I can factor out something. Looks like I could factor out a 1/6 x. So let's see, what's 36 divided by 1/6? 36 divided by the quantity 1/6 is 216. Yeah, so that'd be 216 minus x cubed equals 0. And now I've got the 0 product principle, so either that's 0 or that's 0. If the first one's 0, that would mean that x is 0. And if the second one's 0, that would mean that x cubed equals 216, so x is equal to 6, I believe, right? 1/3, right? 1/3 exponent there, yeah, 6. Okay, and so if x is 0, y is 0. And how did I get that? Right there, I'm doing a back substitution. And if x is 6, then y is 36 divided by 12, which is 3. Now, technically, this is a candidate point, but it's not one that I'm very concerned about, because think about what this means. Our job was to maximize profit. That says make nothing. Pretty sure profit will not be maximized if you make nothing. So I'm thinking that this is going to be my maximum profit, but I still want to make sure. So I'm going to do that discriminant business. But before I can do that discriminant business, I need those second derivatives. So what is p sub xx? I'm going back to here to get that way up top there. P sub xx is negative 6x. P sub yy is going to be negative 48y. And p sub xy is 36. So then plugging it in, I get that the discriminant at the point 6, 3 is going to be xx, so negative 6 times 6 times yy, which is negative 48 times 3, minus xy squared. So that's negative 36. 48 times 3 is 144. Negative 144 minus 36 squared. Pretty sure that this is bigger than that, so that this is going to be greater than 0, because that's all that matters. You can check it or calculate if you want. So greater than 0, but xx was negative. So let's go back and look at our rules. The discriminant is greater than 0, but the second partial xx is negative. That means we're here, so we did find a maximum. So that means that for this problem, profit will be maximized when x was 6, but what did x stand for? Tons of steel. When 6 tons of steel, and y was 3, so 3 tons of aluminium are produced. Do they want the maximum profit? Oh yeah, we got to find that value. So the max profit is, so I got to go back up here and use that equation. So if I bring up my calculator, clear, I need 36 times x times y minus x cubed minus 8 times y cubed. 216,000. Okay, that brings us to the end of section 17.3. Maxes and minimums. All right, I'll see y'all back here for the next section, which is 17.4. Have a good one.